Today, we're going to finish it up with battery tests. We're also going to look at hybrid batteries, specifically how they're put together, and also how we test hybrid batteries. So we're going to do that, and then we'll shift gears and get into starting and charging systems. And the starting and charging system PowerPoint is going to be really one of the first PowerPoints that I use in this class that's actually created by CDX that I've added content to compared to the ones I've created that I may have brought some CDX content into. CDX does a good job on starters and alternators, does a good job on the rectifier system, some great animations. And that basic understanding of a charging system or starting system is really, really important. For example, I just put a new battery in my tractor. I'm checking my charging system because I was suspect it wasn't working correctly. And sure enough, it's not. And so I have the factory manual for it. So I open up the manual and I go to the alternator, and all the diagnostics are for an alternator that's not the one that's on the vehicle. I have a 2-wire alternator with an external voltage regulator, and all the diagnostics are for a 3-wire alternator with an internal voltage regulator. So completely different. So I do some digging. I finally found a wiring schematic because I know based on 2 wires, it has to have an external regulator. So I'm looking through, find, yep, external regulator. I proved that the regulators could. The other clue was that when I unplugged the alternator, the alternator light's still on, which it shouldn't be. If the regulator was in the alternator. So I'm back through, I find the regulator, I find how it has to be wired. And I found, some severe corrosion, in a terminal. And I also found that as soon as I attach the power probe, it collapses the circuit down to about 6 volts. So even though the power probe's fairly high impedance, it's not as high impedance as my scope is. So when I first connected, it says like 13 and then instantly drops down to 6. It's like, okay, I'm definitely pulling just that little bit extra through and it's collapsing the circuit. So with no load on the circuit, the regulator sees that it's charging, but there's no amperage really happening because of this high resistance. So now I'm gonna have to get the scope out and find where my electrical connection is, because I know the regulator, if I unplug the alternator, turns the charge light on. When I plug it in, it turns the charge light off. So I know the regulator itself is at least recognizing that circuit and controlling the charge light and has power. So I got a wiring schematic. I know based on what we're going to talk about in the next chapter, how charging systems have to work. And from there, I'm able to ask questions on how this one works and come up with a test plan. And that's not uncommon. If I'm working on, a vehicle, odds are I'm going to have some good information. But guess what? Sometimes manufacturers change something and the books don't get the memo. Or sometimes the books, whoever did the book copy and pasted for the wrong car and the stuff for your car isn't there. So these basic things of testing batteries, testing charging systems, testing starters are really, really important because they're universal, whether I'm working on a diesel tractor or whether I'm working on, a Toyota. The principles are universal. How certain things are wired is pretty universal. How things are controlled is pretty universal. How a circuit works, how a series circuit works is universal. So it allows us to ask the right questions to come up with a test plan to fix our problem, short of, I'm just going to buy a new alternator and a new voltage regulator. Well, I could do that option and spend the $450. But guess what? I found a melted connector already. So conceivably, I could spend the $450 on parts and still have a broken vehicle. So it makes a lot more sense for me to step back, take the time, and do a little diagnosis. And, hopefully this class helps you with the discipline to do that. Instead of just, well, this is too hard, I'm just going to start putting parts in because that's probably what it is. Well, a lot of times we get lucky. That is what it is. But then there's the time you're out a bunch of money. It's still not what it is. And I don't want to be in that situation. So the battery tests we're going to finish up on today are voltage leak test, static voltage test, parasitic load test, and then the hydrometer test. So a battery leakage test, what we're actually checking for is battery leaking out of the case. So the terminals are sealed, the case is plastic. However, if I have battery acid on top of the tray, it can allow an electrical connection to be made between positive and negative. or even between a positive and ground, for example. So I can actually check the voltage between the negative terminal in the battery case or the positive terminal in the battery case. I can go either way, and realistically, I should go both. And in this case, we're leaking a volt out through the case. So this is a drain on the battery because it's dirty. So this battery is going to go dead just sitting here because it's dirty, and we now have an electrical path, although there's enough resistance that there's only 1 volt there. There's an electrical path where we're losing energy that should be stored in the battery outside the battery. So this is an example where batteries will self-discharge. Have any of you heard that you should never store a battery on the ground? You ever heard that? An urban legend, if you put the battery on the ground, it's going to go dead. So
No.
you haven't heard that one. Okay. Well, good thing you haven't heard it, because it's not true today. In the old days, when all batteries were dirty because they all leaked water because they were not maintenance free and they all had acid on them, if you put them on concrete, they would go dead because the concrete would make the electrical connection and the battery would discharge. On mono batteries, since they should never leak, I can put them on the ground all I want. Matter of fact, a lot of times we actually store them on the ground. It's a non-issue. So there's nothing magic that, because the old thought was, gee, the ground pulls the energy through the case, so I need to put it on a piece of wood. And I actually got yelled at when I first got in the automotive industry for putting a battery on the ground. And so you see people put a battery on wood or put it on something so it's not touching the ground, because the battery will go dead. No one was really asking why. And the reason why is because the battery was dirty, so the ground would complete the circuit, and ergo it would go on, especially if it leaked at all. The concrete would leak under the battery, make a connection, where on wood, the wood would absorb it and keep a connection from happening. If you think about it, we put batteries in metal trays. Isn't metal pretty conductive? Isn't, I mean, it's like there came a point where this thing of don't do it, because the magic goes out of the battery to it became, wait a minute, I can't put it on concrete, but I can put it on metal, and it's okay on metal, but not on concrete. This just isn't making any sense. So let's look at what happens. Yes.
Yeah, I saw some of the batteries and some of the cars on the case that they put some wood on the bottom of the case where they sit the battery.
They put some what? Glue?
Some wood.
Oh, some wood. Yes.
Yeah.
Again, going to that old wives' tale of somehow it needs to be on wood or the battery will go dead. Well, let's think about it. If it needed to be on wood, don't you think the car manufacturer would have put wood there? Just saying, right? You know, I know they want their cars to start when they're on the showroom, when they're trying to sell a new car. That car is probably several months old before it gets purchased. It's been sitting there the whole time. They want the car to start for you, because if you buy a car, the battery keeps going dead, you're not going to be happy with your new car. And that's kind of where I mentioned yesterday about the battery temperature sensors, because some people do put wood underneath there. Now the battery temperature sensor doesn't read the temperature of the battery correctly. Now we're going to overcharge the battery because it doesn't know the battery's getting hot. And we're going to ruin the battery because someone put wood underneath the battery, between the temp sensor and the battery on a car that uses that. Mm-hmm. So what I always say is, if you want it to last a long time, keep it original. Mm-hmm. You know, so if wood was such a great idea, someone would, the manufacturers would be putting wood there. It's not like they don't have availability to get wood and they could put a thin piece of wood in the battery tray or whatever else. I mean, there was a time when this stuff was made out of wood, because we used to make car bodies out of wood and just coat them in sheet metal. I mean, so we've had wood for a long time, and we've moved away from it to steel, to better products. So if it is dirty, wash it off. It talks about in the book about using cleaner and water. You want to, this can become an issue. If I use cleaner, that's going to break down the battery acid. And since I have caps in the top here, what are the odds that some of the cleaner is going to get in the battery? Fairly good if I completely dump this thing with a whole bunch of cleaner and water, right? So now I have a clean, bad battery. So a lot of times we'll wipe it off. We use a cleaner on a rag and wipe it off and things like that to get rid of that acid, but we're not dumping it in soap and water because we run a high risk of that getting into the battery. So there's a case of what sounds really good in the book and what happens in the real world are two completely different things. And again, common sense, the secret weapon we all have. Let's think about it. If I got stuff that neutralizes battery acid and I'm washing the top of the battery and the top of the battery is not sealed, that's how we got the acid there in the first place. Is some of that neutralizer going to get into the battery? And when it does, is it now my battery doesn't work? Yeah, exactly. So like I said, now I have a clean, bad battery. The recycling guy will be happy. I see we got a Monster hat on today. You guys deliver Monster also? Is that one of your products?
Yes, it is. One of the many.
Yeah. Yeah, I go through the white Monsters cases at a time. So
Good to know.
yeah, there was a time when, because it says you shouldn't drink more than 3 in a day. So I'd only drink 3.
Oh, I don't drink Monster at all.
Yeah, well, when I was working full-time in the shop and teaching 4 nights a week, I drank 2 44-ounce iced teas, 3 Monsters, and if I worked in San Diego, I drank a Mountain Dew on the way home.
I'd rather drink coffee.
That was just to keep my car from falling asleep and hitting a tree on the way into Fallbrook. And as soon as I got home, boom, I'd be out.
Wow, run out of juice, huh?
Run out of juice. People say, doesn't that make your heart rate? Doesn't that be up? No, it just keeps me conscious.
Good. I just drink coffee instead.
You said you drink Monsters now? Still?
Oh yeah.
All right, good.
Yeah, I try to limit it to 1 a day now. I'm at home. I may have 2 today because I got to teach till 10 o'clock at night, which is way past my bedtime.
Oh yeah. Long day.
Long day because I wake up like 4:30 in the morning. So 10 o'clock at night's a long day when you're up at 4:30.
That's when I go to bed around 10:30.
Yeah, but you're not getting up at 4:30 in the morning.
No.
Right? I mean, it's one end or the other. And around here, we're an early house. So late night.
I'm on your schedule for sure.
Yeah.
Excuse me, sir.
Yes.
That in the picture it says 1.5.
1.05 volts. Yes.
Yes. How long it takes for that battery to get totally discharged? A day or 2 days?
Depends on what the amp hour capacity of the battery is.
Okay.
Right. So it depends on how much the battery has in it. Its stated charge. How good is it? It can be, it can be a few days. It can be several days. It can be a day. The point is we're checking to see if that's a problem. What I can tell you is we rarely have this problem today. We had this problem a lot before we used maintenance-free batteries. Now, a lot of commercial 6-volt deep cycle batteries are not maintenance-free. So you'll still have this, issue. So battery voltage check. If all I have is a voltmeter, I can still figure some things out. I connect a voltmeter across the battery posts. My open circuit voltage should be 12.6, 12.7. So that tells me it's pretty well charged. If I turn the headlights or blower motor on to provide a small current load, should still have about 12.5 volts. So if I turn the headlights on and it goes from 12.6 down to 11.5, guess what? Your battery's junk. All it has is what we call a surface charge. It has some voltage on the surface, but nothing behind it, no current capability. So again, I can use a voltmeter to get some rough information. If I'm out someplace and my car doesn't start and I don't have a voltmeter with me, I can turn on the headlights. Are the headlights bright? Let me try turning the car. When I turn the car to start, do the headlights get really dim and it doesn't start? Or do the headlights stay bright and it doesn't start? Well, if they stay bright, the starter's not trying. If they get real dim, the starter's trying, but there's not enough power in the battery. So you can see where we can, again, that secret weapon of common sense. Let's ask a couple questions, use the tools we have and figure out, a direction. Because we don't always have all the tools with us. I mean, when I get stuck somewhere in my car, I don't have my toolbox with me because my toolbox doesn't fit in my car, first of all. But I don't have every tool I want with me. So I need to, be able to kind of figure out using logic how things work. Yeah, Jess.
A bad alternator is not gonna prevent you from starting your car, right?
Correct. A bad alternator will not prevent you from starting. However, it could be the root cause of your dead battery that is preventing you from starting. So if the car doesn't start, replacing the alternator is not going to make the car start. However, if the car doesn't start because the battery's bad and you charge up the battery and figure out that the battery comes back to life and it's good, now the car starts and the starter works, then you check the charging system and find out the charging system is not working. Now you have the root cause of what caused the no start. So no, the alternator will not prevent the vehicle from cranking over. It will not prevent it from starting. It will prevent the battery from being recharged and having enough energy to start the car. So that's where that happens. So if someone's putting an alternator in a car that doesn't start, thinking that the alternator is going to make the car start, you're at the wrong end of the horse here. So but that's why we always check the battery first, because once I know the battery's good, then I can test starting next, and then I check charging last. And so we always do it in that order: battery, starting, charging. And it makes sense because I have to start the engine to check the charging system. So, right, I need it. So it makes sense to say, I got to have a good battery before I can test the starting system or the charging system. So we start with the battery. So that's where that you'll see, and we'll see this when we get into cooling system, when we get into other systems. The process of diagnostics should be really fixed. It should be, I do this, then I do this, then I do this. If I do things in the wrong order, say the car comes in running and the customer says, I'm afraid to shut it off because it won't restart, but I think it's my alternator. Can you check my charging system? And you check the charging system and go, yeah, you're right. The alternator is not putting out the right voltage here because, the battery's only got 12.6 volts or 12.4 volts. Your alternator is bad. You go put an alternator in it, the new alternator may work the same way because it's actually the battery making the alternator look bad, or it's a connection making it look bad. If the battery's not good, the charging system's not going to work correctly. So working in service stations and having made this mistake, because you have customers say, I don't want to turn it off. I don't want to turn it off. We finally had to tell them, look, you need to turn it off. We got battery chargers here. We got things here. If it's a bad starter, it's a bad starter. We can't tell that with the engine running. We really need to turn it off and do the full test. And once we started doing that, we started making a lot fewer mistakes. When we do things out of order, we're going to make incorrect conclusions every time. And I don't care if it's a cooling system problem or starting charging system problem or anything else. It'd be like checking for oil pressure and saying you need an oil pump because there's no oil pressure, but we never look to see if there's any oil in the engine, right? Kind of step one is there any oil, right? So before we condemn the pump for not pumping any oil, let's make sure there's some there. And that's, that sounds silly, but I see people make really that big a mistake. Yeah, Christopher.
Yeah, so I got a little bit of diagnosing that I have to do myself. So I was out of town, I don't know, a couple months, and my car was here sitting. When I returned, I couldn't get it to start. I knew it was the battery because I didn't have any kind of lights, no alarm, no power. So I took it to AutoZone. They charged it. I put it and dropped it back in. When I dropped it back in, I noticed one of my interior dome lights was on. So that's probably what caused it to die in the first place.
Could have, yeah.
And then so I put it in, I started up, I let it run for a little while, and then I kill it. And then I want to say like 2 days later, I go back out there and it's dead again.
Okay. Completely dead?
Completely. Same thing as the first time. Completely. Okay. No
So
alarm. Nothing.
It won't light up a light, won't light any dash lights, nothing. You're
nothing.
DOA.
Yeah,
Okay.
Exactly. So I take it to AutoZone again. They charge it. They're like, oh, it has a bad cell. I had originally got the battery from Walmart. So I took it to Walmart. And fortunate enough, they just replaced it because I had got the 5-year warranty and it hadn't been 3 years yet. So they did that. So I just dropped it back in and it started up fine. But now I know I need to do the diagnosis process because the battery shouldn't have just died on me like that. But I don't know if it was because I let it sit for like a month and that dome light was on. That might have, killed the battery or ruined it to where it couldn't, hold the charge.
And that's certainly possible, especially, they're saying you got a bad cell in it. And that's why I'm always suspicious, because they charge the battery, they look at the surface voltage, but a lot of times they're not testing the battery effectively. When they give them back, because like my neighbor had a battery in his car, and he went down different auto parts store, but same thing, and took the battery down, and they kept charging it and telling him it's good, charging it, telling him it's good, but his car wouldn't start. I bring over my tester, check it, the battery's no good. So he's been down to the auto parts store 3 times with his battery. They keep telling him it's good, and it's where he bought the battery from. It was under warranty. They keep charging and tell him it's good. I put the tester on and go, see this? The battery's no good. And he had to actually argue with them and go, look, do you want, my neighbor's, Master Tech, yada, yada, yada. He used his tester on it. It's bad. And he explained why. And I actually used the carbon pile tester to find the problem. And it had a bad connection between the cells. So yeah, that's certainly possible. What I would do is I would do a parasitic draw test on it to verify you don't have something pulling the battery down. And that's one of the next tests we're going to get to. And that if I had a car that goes dead in a couple of days, even though the battery's bad, I'm still going to do that parasitic draw test, especially if you found a dome light on, Lord knows what else could have been kicked on, or transistors stuck or relay stuck. But you want to do that parasitic draw test. And that's going to tell you right away whether the battery discharged itself, which they can do, or whether when they're bad, or whether it had something outside drawing it down. So a bad cell can actually cause a battery to self-discharge. So did that help, Christopher?
Sorry, my internet cut out on the last part that you were saying.
Okay. So like I was saying, a battery can self-discharge if it has a bad cell, but you're going to want to do a parasitic draw test and verify there's nothing else drawing it down.
All right, and that you're gonna go over.
I'm going to be getting to that, I think, in a couple tests. So we're right around the corner from it.
All right, awesome.
Okay, so a hydrometer check. So I mentioned before a hydrometer, and you're going to see on the next slide someone actually pulling liquid out of the battery. And what we're doing is we're looking at the specific gravity, and based on the specific gravity, we know are we at 100%, 95, 75, 50, 25%. However, I got a nifty voltmeter, and if a 100% state of charge is 12.6, 12.7 volts with 0 amps on the battery, in other words, open circuit voltage. Oh, could I use my voltmeter? And if my voltmeter says I have 12.7, is that a good indication that I have a good state of charge? And I didn't pull any liquid out. How about if I only have 12.5 volts? Okay, that's more of a sign that I got a 75% state of charge. 12.4 volts, only a 50% state of charge. 12.2 volts, a 25% state of charge. So again, I can use my voltmeter, take the knowledge that we've learned from hydrometer testing, knowing that if my hydrometer reads this is how many volts I'll have at the battery. Why don't I just go get the voltmeter and go, you know what, if I only got 12.2 volts, my battery doesn't have all of its charge. The battery needs to be charged, or there's something going on. If it keeps coming back to 12.2 volts on its own when it's just sitting on the shelf or not connected to anything, I've obviously got a weak battery. I've got a battery that's worn out or on its way out. So I can use the voltage here, my open circuit voltage, with a voltmeter to really tell me the approximate state of charge of the battery. Well, if I can use a voltmeter for that, why should I get something out, pull fluid out? You see how much battery out, how much electrolyte we're pulling out. We're pulling out quite a bit. We're looking at where the little pointer is. Then we try to put it back in and move to the next one. Well, some of it's going to dribble. Some of it's going to mix. So, I mean, if I'm working on something where I got, say I got 6 times 3, so 18 cells, because I'm working on 6-volt batteries. They're in series. And anytime we're in series, it's only as good as its weakest cell. If I'm trying to get a golf cart to work as good as I can, I'm probably going to go through it. I'm going to, first of all, I'm going to check the surface voltage on each battery. I'm going to disconnect them, or I can even do it in series and see if they're all supplying the same amount of voltage. If they are, I don't need to do anything. If one isn't, now I need to see, do I just need to replace it, or can I adjust it? So a lot of times they will have acid there that they can add and adjust and things like that. And that's one way they're able to get 10 years out of these deep cycle 6-volt batteries in marine use or in an off-grid solar system or something like that, because every 6 months or so, they're going in and spending a day, kind of balancing the battery cells, basically. So that's the only time we do this. I mean, the days of doing this on cars are gone. We don't do this anymore. Why would you? So we can do that. You can also use a refractometer where you take a smaller amount of fluid, you put it on a lens, and then you hold the back part of that up to your eye where you see the light and you see a line in it. I'm going to show you that on the next picture to give you this state of charge. Now that you're taking liquid out, it's not going back, but you're not taking very much liquid out. You're using a drop or just a couple drops. So unfortunately, education in books is still really fascinated with this. It's like students have to know it. You can't test a battery without it. Students have to know the chemistry. I think it's important to know the chemistry happens. But if I told you it's positive and negative pixie dust, and as long as the pixie dust stays on its own side, your battery's charged. And if it gets all mixed together, your battery doesn't work. Is it really going to change how you fix the battery? It's probably not. So we tend to kind of get into over engineering terms sometimes. And I don't see Preston here this morning yet, but Preston was talking. He was struggling with some of the math on some of the series parallel exercises. And he found, I think it was an engineering site or a physics site or something. They showed him the real hard way to get there, right? Because I mean, they made it, a 20-step process instead of a 2-step process, right? Because somehow you need to know that if you're going to be in physics, and maybe you do need to know that to be in physics, but you don't need to know that to fix it. So, and that's where I get to. So I have this here. I talk about it. And the big point is I explain to you why we don't do it and why it doesn't make sense to do it, why you shouldn't go buy this tool. Because even if I find one that's low, I can't get battery acid. Okay, so if I can't get any acid, how am I going to fix it anyways? Oh, that's right, I'm going to buy a whole battery. So why don't I just test the whole battery together, and if it's bad, I'll get a new one. Here is the refractometer. So we put a little drop or two on the lens, hold the lens up to the light, and based on that, we can see where we're at. In this case, 12.75 is fully charged, and we're up at almost 13.5. So you can see the scale here. So it's not exactly as precise as what we were looking at. So let me back up. Right, because we are at 12.65, 12.5, 12.3, 12.0. Here's 12.0, here's 12.5, 13, 13.5. This has a huge surface charge on it. This is not in the normal range. Or they used a picture when they're looking at coolant, and it's not even battery acid on the picture. So someone grabbed the picture and didn't know it, which is also real possible. And I would highly suspect that. But how do I know there's anything 13.5? Where's 13.3 in here? I'm kind of guessing, right? It doesn't have the accuracy on this particular one to do that. So we can buy these where they do a lot of different things. Like this one does both coolant, both ethylene glycol and propylene glycol coolant. And we do use this for coolant. And when we get in the cooling system, I'll talk about this a little bit more. But they can also do battery fluid. They can do windshield washer fluid. We use them. I have one that I use. It's calibrated. It's used for DEF fluid, diesel exhaust fluid, for the AdBlue, for the diesel fluid, because it has to be 32.5% urea. And if it's not the correct percentage, then you'll get codes and things don't work right. So we actually have to check that to make sure it's got the right content before we go down the rabbit hole trying to diagnose the system. This is the tool we use that, but again, it's got a scale just for that. The scale is widened, so I'm not looking at this, I'm looking at this. I can actually see it's a full scale, so I can actually see the difference between 32% and 30%. It's not scrunched up really small. So, a lot of times people have more than one of these, one for coolant. If you're doing batteries, I'll have one that just has a battery scale in it, or one that has, the main scale is a DEF scale, things like that. Because you need accuracy in what you're measuring compared to something that this is pretty accurate for coolant, is what you can see, not as accurate for battery fluid. So here we're trying to do a precise test on specific gravity, yet our tool is not precise. And really, so I'm at 13, 12.5 or 12.0. Is that telling me anything more than a voltmeter did? You got a high surface charge, because sometimes a high surface charge, what I mean by that is sometimes after we charge a battery, we may see a battery has 13 volts or 13.3 volts when we turn the car off. And we know a fully charged battery only has 12.7. So that's a surface charge because our charging system works at a higher voltage. So if you turn on the headlights for like 10 seconds, 20 seconds and turn them off, now all of a sudden you're going to be down in that 12.7, you're going to be at that normal range. You got to take that surface charge off. So if someone does a hydrometer test when there's a surface charge, again, the test is not accurate. So that's why we don't do it. But the idea of this class is to educate you. So instead of just saying, we don't do that, or, oh, we don't teach that, why don't I explain why we don't do it? And then it makes sense, because you may go to another class, or you may have another instructor, or talk to someone else who says, oh, we always do it this way. And they might have a reason for it. It might be because we've done it that way forever. They might say, well, it's the only accurate way to test it. Really? Yeah, it is the only accurate way to really test a cell, but why do I care unless I'm working on a big series battery? And so sometimes the only way to do something, if there's no reason to do it, why? Testing battery state of charge, conduct an open circuit voltage test, select volts, DC position on the digital multimeter, and attach the probes to the battery terminals, red to positive, black to negative. Compare the reading to those given in the previous slides. So again, what do I got? What is that? 12 point, it's like 12.28. So we call that 12.3 volts. Go back to our previous chart. 12.3 is going to be right in here. So we're a little under 50% charge. So this is either a battery that's on its way out, or I have another problem that it's not charging it. Weak charging system, car's been sitting a long time, something like that. So I'd want to charge it and then retest it before I do other tests. Otherwise, if I only have 12.2 volts and now I go test the starter might test bad. I go test the charging system might test bad. So I want to charge up the battery, see if the battery comes up to that 12.7 volts. I'm good. Even 12.5 I can live with. That's 95%. I'm good there. Now 95%, so 12.5 or higher. Now I can go test other things and trust the results I get. However, I put on the charger for a half hour or an hour at low charge, come back, I've still got 12.3 volts. This is an old battery. It's not going to hold any more than that. It's lost some of its capacity. So it may still be starting the car, but don't confuse this battery is good. And I've been able to figure that out without a Midtronics tester, without a carbon pile tester, without anything, because guess what? It can no longer hold 100%. There's a hole in our battery's capacity that it fills up at 50%, and then everything else just goes away. And many times when that happens, the charging system may try to put more energy in, and then the battery overheats. You actually look at the size of the battery and they'll be pooched out. So if I got 12.3 volts, I look at the size of the battery, they're pooched out. It's really looking like it's battery day to day. So, right, the preponderance of the evidence, as I call it. So a 12-volt battery with 12.4 volts and no loads applied is approximately what state of charge?
75,
Is that 75? Let's see.
50.
50.
50. Boy, it doesn't change much between 75 and 50 on voltage, does it? And this is one chart. Interstate's chart jumps down a little bit. I think they're 25% at 12 volts. So there's not 100% consistency on these numbers, but it gives you an idea. And the point is, if you have 12 volts and a 12-volt battery, your battery's dead. And that's really the take home I want, because the kid at the auto parts store probably thinks that 12 volts is a charged battery because it's a 12-volt battery. You bring it in and it's got 8 volts. Now it's got 12. Hey, I charged your battery up. But once we know it's not charged up till we get to 12.6 volts, and now that makes a lot of sense. So while you might have a battery that reads 12 volts, but your car's not starting because there's nothing in it. It's just got some voltage, no amperage. No wonder why that starter's not working. So think about how many people have probably put starters in, battery cables in, all kinds of stuff in, because their 12-volt battery reads 12 volts, but the car doesn't start. a lot. Back in the early days, when I first started working on cars, you're probably looking at one of them. You know, when I first started working on cars with friends and doing that before I went to school, I didn't know any of that stuff. It's got 12 volts. Why isn't it starting? And you learn just enough to be dangerous, right? You learn just enough about things to be dangerous, because we spend a lot of time teaching people how to do a test or how to replace a part, but not necessarily how to think about whether that test is accurate or not. So parasitic loads. Current draw present when the engine and all electrical devices are off. So in other words, when I take the key out of the ignition, shut the car off, car's off, close the door, it's locked or whatever it is, and I walk away. Anything that's drawing energy out of the battery at that point is what's called a parasitic load. So parasitic loads are designed into two categories. One is intended parasitic loads. So there's our vehicle alarm, our clock, our computer memory, those things. So a newer car is going to have a higher acceptable amount of parasitic load than an old car. Over time, regardless of how big this load is, it will drain a 12-volt battery enough to prevent starting. So if I look at my parasitic draw, I need to be able to test that with the doors closed, with everything off. The other thing I need to be conscious of is that it takes time for computers to go to sleep. So I may have a high parasitic draw for 5 minutes, 10 minutes, an hour and 20 minutes. I may have an unacceptably high draw, a couple hundred milliamps. But eventually, I should get down to under 25 milliamps unless the manufacturer provides a higher number. Okay, so if I'm under 25, that's not going to cause my battery to go dead, but for several weeks, if not a month. If I'm over 25, I need to look up the spec. Generally over 50 is considered definitely bad, and it's going to start draining it pretty quickly. Some manufacturers, some Mercedes models and stuff are allowed 70. But you're talking very, very small numbers, but yet it can draw a battery down over a weekend. So it really happens pretty quickly. And this is a big issue. I used to work by the airport back in the early 80s, and people would leave their cars at the airport and they'd come back 4 days later, 6 days later, 10 days later, and guess what? The car didn't start. And so we did a lot of service calls over at the airport parking. That's when you could actually park at the airport, and things were a little different then. You could actually get in and out of the airport to do a service call. It's crazy, crazy times. But this is an issue. So we'll check for abnormal current draw, high parasitic load with the key off. We're going to make our amp meter connections, close the doors and trunk, turn off all electrical components. We're actually going to close the doors, trunk, turn off all electrical components before we make the amp meter connections. We're going to disconnect the underhood light bulb if it's there, and read the amp meter and compare the reading to specifications. So what we're going to do is and I normally do this on the positive side, not the negative side, although we know it doesn't make a difference. So it's really whatever's easiest. But what we're going to do is we're going to hook our amp meter. And I normally just use amps, and I can always go down to milliamps. I like my graphing multimeter for this because I can look at a graph over a long period of time and watch it go from high. Oh, this computer went to sleep. This computer went to sleep. Now I'm here. I can come back 5 minutes later and see, because I can put on a 5-minute screen and come back and look at multiple screens. So I don't have to sit there and watch it. I can walk back and, oh, it's low. Let me stop the recording, back up and see, oh, where did it go low at? I can look at the movie. So I like using the Vantage for this because I can graph. So that's one of the advantages of using this of graphing. Inductive clamps do not work well for this because we're looking for such a small amount of current flow. They do make some inductive clamps that are sensitive enough to do this with. They're like $500 compared to the $100 clamps that I showed you. So they came out just as I was leaving industry, and I wasn't willing to spend $600 on one at that time. And I keep waiting for them to come down in price, and they're still like $500. And for not doing this every day, and I can still know how to hook in line, I'm not spending money on that. But what we're doing now is now everything on the car is powered through the meter. So this is measuring all of the current that the car is using. So if you open a door and those lights come on when you're doing this test, you might blow the fuse in your meter. Are you following me? Because now you're running the whole car through this meter. You turn the key on, I guarantee you're going to blow the fuse in the meter. So we do all this with the key out, doors closed. I normally put the windows down so I can kind of look inside or see things. And I'm going to see a number here. If I read 0 here, odds are the fuse is blown. Okay. If I'm curious if it is the fuse that's blown, I can turn on like a dome light manually, or I can turn on one light bulb, because I can certainly power up a light bulb or 2 light bulbs and not be over 10 amps. And if I turn the light bulbs on and the light bulbs don't come on, that's a sign the fuse inside here is blown, because we're no longer making an electrical connection. Right? And this happens all the time. We go to do a test. Hey, it passes. This is 0. Did you check and make sure your meter's working? Right? Because odds are you're not going to have 0. You're going to have, probably, you're going to start off, especially on a newer car with a computer, you're going to start off with, 100 or 200 milliamps. It's going to may quickly come down to under 50 milliamps. And you'll see it cycle down to under 25 milliamps. Even when everything's shut off, I should still see 5 milliamps, 10 milliamps, 20 milliamps, depending on the vehicle. I shouldn't see 0, because 0 would indicate that what? You have no computer, no clock, no alarm, no remote, right? That I can push the button and unlock my car, because that computer has to stay awake. So you see why 0 is instantly. It can't be 0. It has to be something. It may be 2 milliamps. I've seen 2 milliamps, but it has to be something. Now, if I have a issue and it's too high, at that point, what I want to do is start isolating the fuses that are hot all the time. I don't need to worry about the fuses that are hot with key on, because guess what? The key's not on. So I go through the fuses that are hot all the time. I take them out one at a time, and I look to see, does this drop when I disconnect the fuse? If it drops when I disconnect the fuse, then what I can do is put this back together, take the meter over, and now I'm going to put it where the fuse is. And I'm going to take the wiring schematic and go down to all the things that fuse disconnects. But the advantage now is I can probably open the door. I can do some other things. So that's how we do it. We kind of start at the trunk of the tree, we go out on the limb, then the next branch, where we finally get to the leaf that's causing the problem. And that's how we diagnose parasitic loads. So parasitic loads can be, difficult for some techs to diagnose. It's really about patient, and it's really about just understanding. I'm going to start here, then I'm going to go here, I'm going to go here. You also got to keep in mind circuits that are not through the fuse box, but have power all the time, like the alternator. So bad diodes in an alternator can cause a parasitic draw. It's unusual, but it happens. So if all the fuses are out, because they're easier to get to than disconnect the alternator. Okay, all the hot all the time fuses are out. I still have a draw. Now I need to look for things that don't go through a fuse. Alternator, what else do I have, right? So you're just trying to look at those things. And that's where a wiring schematic is so important for that. But, common thing to have to diagnose. Yeah, Jess.
So I've done this test before, to find, well, it was my stereo that was draining it. But my question is, if I were wanting, because there's different fuse box locations, like you have one in the hood, one here, one in there. Isn't there like a master unplug for each of them?
Well, usually there's multiple fuses in series. So there might be like a 100 amp maxi fuse.
And that controls it all.
It might control 5 or 10 fuses. Then there's another 60 amp maxi fuse that controls another 5 fuses. So you're probably going from the battery to some hot all the time fuses that are bigger fuses. Then they go to smaller fuses that may or may not be hot all the time. So again, you're just kind of going down. That's why that wiring schematic is so important. So you just go to the battery. What's connected to the battery that doesn't have a switch?
Well,
That's pretty
my
much-
question is if I wanted to pull the big ones first, just to narrow down my search quicker.
Right, and that's
You're
what we would
saying-
normally do because it's like here, so let me stop my share for a sec. And let's see here.
So I guess my question would be, you're saying that the little fuses are they're controlled by the big one, or
They can be
Fair enough.
powered by the big one. It depends on the car manufacturer. So
oh, okay. Okay.
let me get in here. Christopher, what year's your Honda?
It is, I have a 02 and a 03, but mine's a 03 Civic. Yeah,
03 Civic, what model Civic?
it's a EX, 1.7 VTEC.
1.7 VTEC, not a VTEC E, just a VTEC, right?
Just a VTEC, yeah.
Okay, back up here, hit the wrong button. Okay, so let me share the screen here. So I'm in all data. I've identified the vehicle we're working on. I'm going to go to power and ground distribution. And see, I have fuse boxes, relay boxes, fuse, grounding point. And what I'm looking for is where it at. So I can go to OE diagrams here. Power distribution. So you see where it pays not to get distracted by all these things right now. I got to look at these when I want to go to the fuse box for fuse locations. I may go here, but right now I want to look at the diagrams and I want power distribution. A lot of pictures, right? So I got 10.0 all the way to 10.11. I have an index here and it gives me all these different fuses for power distribution. But somewhere in here, we should be going to the battery, which is 10.0. So here is the battery. Let me find where the battery is. There's the battery right here. I have the positive terminal goes over here to the starter solenoid, and then it comes over to here in my underhood fuse box. It goes out to diagram 10-1A, and it feeds directly this fuse, this fuse, this fuse, this fuse. I got to go to 10-1B, this fuse, go to 10-2, this fuse, and go to 10-4. See how there's no switch between the battery and these fuses? That means they're getting power all the time. So from here, I need to what? Go to the next picture. So I should have a next here. Yeah. See next diagram. So here, A from the first diagram comes in and I have a fuse here, here, that's not used here and here. These are all hot all the time fuses. So you can see on this Honda, it's feeding a lot of the fuses. Here we go, hot all the time. And it's coming down to what? So this fuse number 9 in this case, which is hot all the time, it's feeding the immobilizer, it's feeding the DLC, audio, gauge assembly, keyless entry. It's feeding all of these things. But by disconnecting the fuse, I'm able to figure out, is my problem one of these things? Are we following the logic there? So if I pop this fuse and I still have my draw, guess what? None of these are my problem. That's why we go to the hot all the time fuses next. And then once I pop a hot all the time fuse and I watch the meter go from like 100 down to 2, bingo. Now I need to go back to the schematic. What is that fuse feed? Now I need to start looking at these and figure out where's my next test point. So in this case, this is a splice inside a relay box, which is going to be difficult. And then it goes to these different units. Oh, wait a minute, is something plugged into the DLC? Oh, the customer plugged a piggyback programmer in her that they didn't tell me about. And the real DLC is hidden underneath the dash, and it's a second DLC that I can actually see. It's not even the right one. I've had that happen. Do they have a gauge package or something attached to the DLC that's not turning off because they wired it wrong and it doesn't know you turned off the key because they thought battery power is battery power. So one of them is supposed to go to full-time power. The other one's supposed to go to key power so it knows when to shut off. And they just said, oh, 12 volts is 12 volts. I'm just going to put them both together because I'm so smart. And they created a parasitic draw problem because now the system never shuts off. Those kind of things gauge. So it kind of comes down to looking at these different things. The other thing that we ask, because obviously it takes time if I had to go to the immobilizer, DLC audio unit, gauge assembly, keyless receiver unit. One of the things I would check for is, does the remote key work? Gee, this doesn't work and I have a draw. Oh, the immobilizer didn't work. I bypassed that because it was causing a problem. Right? So a lot of times when things malfunction, that's when they cause a draw. So sometimes knowing what doesn't work can really be helpful in figuring out which of those you want to look at first. Yeah, June.
Right. Can we, as a student, can we get access to your, can you give us access to all data?
I do not have access. This is my account here. I think they got the school account back up. I will see if we can get access to it.
Thanks.
You bet. I know we have access to it when we're on campus. So you can always save that stuff and we can pull it up in the computer lab on campus.
Okay.
So we can always do that when we're on campus. So you can certainly do some research, print some stuff out and bring it home. And we can always do that also. So do you get the idea of how we're going through that parasitic draw process now? Did this help answer the question, Jess? And Christopher, does this give you some input on where you're going today?
It does. Thank you. I kind of have like an idea of the steps, but this gives me like a little, an outline to follow and stuff. I'm hoping it was just that incident, but I like being techs, we got to verify the repair and do the diagnostic process. So I don't want to just put the battery in and call it good. I want to go back and make sure there's nothing wrong with it to cause the situation in the first place.
And going back to Jess's comment about the radio, the first thing we do as a technician, if I have a parasitic draw, is disconnect anything that's not factory.
Copy. So yeah, I have an aftermarket deck too, so I'll probably have to do that as well.
It's real common for amps to like stick on, especially if the battery power gets low. And cause draws. So again, and this brings up a great point. Do I have a broken car or did we put something on the car that's broken? Right? So am I diagnosing the broken car, right? It left the factory, it was fine, now it's broken. Or did I put something on the car that's broken that's now causing the car not to function? So that's why you'll see technicians ask, is there any, aftermarket components? So the first thing technicians may tell you is, well, the first thing I need to do is disconnect your aftermarket stuff. And customers get rid. Well, I know my stereo is not the problem. I know. It's like, look, this is step one. I need to isolate. Is this your stuff that's causing a problem, or is it a broken car? Because my manuals are all about the car. All I can do with your stuff is disconnect it, right? I'm just trying to find out what's causing the problem. And once I disconnect it, if that's the problem, then is it a bad component or was it not, like I said, not connected properly because there's a yellow and a red wire, one's for key on, the other one's for constant power. And they decided since it said 12 volts for both, they'd save time and just put them together. And then the system never shuts off. And I've seen that countless times on aftermarket installs where it's DIY and someone has enough knowledge to go, oh, wait a minute, 12 volts and 12 volts. Why do I need to get it from two different places? I don't want to spend that time. I'm going to get them from one place. So it, so it's not always the product's fault. Sometimes it's the installation. Sometimes it is the product's fault. Let's face it. Aftermarket products, many times, are not built as well as original products are. I put a backup camera, rear view mirror, front camera thing on my 95 Cherokee. And it was like $130 and it was hardwired. I didn't want it wireless. So I wanted it hardwired. So I did all that. I'm under no illusion that for $130 for a screen and two cameras, that it's of the best quality ever. Okay. Just saying. And it does record. I mean, it has recording time and all this. I mean, it has lots of features. I mean, it's a great bang for the buck. But I'm under no illusion that the quality of this product is not what you would get if it came from the factory. All right, let me change share. So parasitic draw testing. Okay. So this is something now, if a car comes into a shop and I'm working on and I suspect a parasitic draw problem, my initial half-hour diagnosis normally covers checking to see if there is a parasitic draw. It does not cover finding the parasitic draw. Okay. One is, do you have it? This is a pretty quick test. I got to wait for computers to go to sleep. So I may have to come back to the car in an hour, but it's not real labor intensive. Either you have a draw or you don't. Okay. And if I suspect one, you know, so I have a car that comes in, my car doesn't start after it sits for a few days, or my car didn't start when I got from the airport. We're going to test the battery, starting, charging system. When all of that tests good, the next thing we do is check for a parasitic draw. If it has a parasitic draw, we're going back to the customer and giving them an estimate to locate the cause of the draw. Yeah, Jess.
What's the ballpark maximum range it shouldn't be? Like it.
There's not so much a maximum range, and certainly it varies by vehicle. Normally, you're going to see someone start at 1 to 2 hours of time.
No. The amp draw. The amp draw.
Oh, amp draw under 25 milliamps is good. If I'm over 25, I want a spec from the manufacturer telling me it's okay. Because there are some cars that, like a loaded Ford Expedition, is allowed 48 milliamps. And I know that because I've looked it up. And we worked on a lot of Expeditions. So I know that some are higher, but if it's under 25, it is not my problem. It is not why this car went dead. So under 25 is a known good. So a lot of the things I give you, I know what known good is. If it's not in the known good range, it doesn't mean it's bad, because there's 1,700 different models of car on the road. I need to go look it up and see, does the manufacturer say this is okay? But I'm not going to go look up everybody. Why would I take the time to look up everybody when I do the test? It's at 15 milliamps. I know that's not my problem. Why should I go spend 10 minutes looking it up? Right? Because I'm at the end of the day, I'm a lazy flat rater. I'm looking to get the most information with the least amount of work. And I don't even apologize for it. Matter of fact, I'll be teaching professional technicians tonight how to be a lazy flat rater on new Fords. So in order to connect an amp meter directly to measure a parasitic draw, it must be connected in what way?
Series.
In series, right, because everything's going through that meter. So causes of a discharged battery: defective battery, cell shorts, low electrolyte, freezing damage. Not a big problem in Southern California. Charging system problem. Poor cable connections. Poor cable connections can actually cause charging system problems. On newer vehicles, because the charging systems on many of them is controlled by the computer, the engine management computer, or PCM. Bad connections to the computer can actually cause a charging system problem. So if the computer only sees 11 volts because there's high resistance on the power side or ground side going to the computer, so it thinks there's 11 volts, it's going to tell the charging system to charge as much as it can. But if the battery, so the battery might have 18 volts in it because the charging system is charging so much, but the computer that's telling them to do it only sees 11 of that because of bad connections. So that's something that, as we moved on to computer control system, is not just the poor cable connections going to the charging system, it's the connections going to whatever computer is controlling the charging system. Engine performance problem, requiring excessive cranking time. So say my car is supposed to start in less than a second, but say I need to crank it 10 seconds every time to get it to start. Is that going to put extra draw on the battery? Is that going to put extra strain on the battery? Sure it is. Is it going to cause the battery to potentially last a shorter period of time? Yes, potentially so. Is it going to cause the battery to possibly have a lower state of charge? Yeah, if I'm doing short trips, I start it up and I only, drive a block or 2 blocks and shut it off. And I have a lot of short trips. It's designed to spend a second cranking the engine over and then get charged back up. We had to crank for 10 seconds and we're not driving very far. So that can affect it. Electrical problem, drawing current out of the battery with the key off. That's our parasitic draw. What causes voltage drop? Remember, voltage drop is caused by resistance, any resistance when current flow is present. So if I have resistance in a circuit and I have current flow, I'm going to have a difference in voltage on either side of that resistance. Wanted resistance is our load device designed into the system, such as a light bulb or a starter. Unwanted resistance is caused by damaged wiring or bad connections. Since the entire car is a parallel circuit starting at the battery, we should always start there when looking for unwanted resistance. So, a lot of people go, hey, the battery cables are tight. Well, there's 2 ways to look at it. Well, yeah, great. They're physically tight. That's important. Not saying it's not. But are they electrically tight? Meaning they have a good electrical connection with little or no resistance. I can have a tight battery cable that's physically tight, but still have a huge amount of resistance in the connection. So when we talk about loose cable connection of the battery, improper cable replacement, corroded battery cable from wicking. So what I have here is I have a battery cable that this actually I cut off a car that actually had battery acid leaking out of a starter.
Wow.
Okay.
It's bad.
Because it was a side post battery. The battery had lost its seal. So the acid was coming out and going right down the cable. And so these are DIY battery cable ends. And we used them in industry for a long time. I mean, you can buy them at any parts store. The problem with them is they do not seal the end of the battery cable. So now you're still going to have wicking or corrosion from that. So a professional repair is going to be sealed. So here's a professional repair. Here's a DIY style repair. So we can see here DIY allows acid to enter the cable. And what we see a lot of times, there's enough cable that I can cut it back and recrimp it when the cable end goes bad. I might be able to do that once, sometimes twice. What we see when people use cable ends like this, we'll actually see the battery acid wick 5-6 inches down the cable, and you can feel it because it's just stiff and doesn't bend. Now you need a new battery cable. Well, how much is a battery cable? Well, like most things on a car, it depends, right? So am I just talking a little cable that's this long that goes from one point to the other? I'm going to probably replace the cable and not put an end on it because I can get a cable for $10 or $15. What if the cable's 3 feet long? Well, now it's worth putting an end on it, but that cable's still probably only $30, $40. Many modern vehicles, that cable is part of the wiring harness and you get the positive and negative cables together. Now we're talking a $450 battery cable. Now we're talking 3 or 4 hours to put it in.
And you want to go bigger on the cable, right? I replaced my negative post cable with a 0 gauge.
Yeah, if I'm replacing cables where it's like a traditional battery cable where it's not part of a harness, yeah, I like to I like to use at least 1 gauge, if not 0 gauge cables. I have some double-aught cables on my truck going to the jump boxes and stuff on it. But I mean, I don't put 4 gauge cables back on customers' cars as a rule if I'm just replacing, because the cost difference is next to nothing. And it just makes everything work better. So, consequently, if the cable's inexpensive, it's not bad to change the cable. If I ever buy a new cable, I better not be able to see the cable between the plastic and the metal end. If you do, it's defective. Give it back to them, tell them you want one that's not defective, because that's going to allow acid to get into the cable. So even though batteries are sealed, even though batteries shouldn't leak, things do happen. And again, it's not necessarily leaking around the seal here, which would be a defective battery. What if someone's overcharging it? Now we have those acid vapors and stuff coming up. That's getting in the cable, right? So we want to have that sealed. So here is one that I put a crimp connector on. and then sealed it with heat shrink tubing. So this is a professional repair right here. And you can see this is a 1-0 cable end, or 1-0 gauge cable end. So I have number 4 cable ends. I have, different sizes down to 2-aught. So we have a whole assortment, and then I'd make the cable, slide the heat shrink over it, seal it. And again, if you're a customer paying for a product, which would you feel better paying? This, looking at it going, you charged me, $40 for that. I could have gotten, my neighbor told me that I could have bought it at the parts store and done it myself, compared to this, which is, yeah, I paid, $60 for this, $50-$60 for this, but boy, this looks professional. This is a good job. And so, I have no problem charging, $50-$60 to put a battery cable on if the new battery is new battery cable is $200, right? If I can make it just as good as the new one, when you look at parts and labor for me to install a battery cable, we're looking at $200. I can fix yours for $60. That's a great deal. If I can buy a new cable and install it for you for $30, I'm ripping you off, charging you $60, right? So I'm doing the same job. The job's still worth $60, but dependent on the other options is going to determine which one I'm going to use, right? Hey, it's $700 to put a new battery cable in. I can fix both your terminal ends, crimp new ones on and heat shrinking. It's going to be $80. Man, I'm your hero. I charged you $80 and saved you $700 because that's what the dealer quoted you. On the other hand, I charge you $80 and I could have put new cables on for $40. I'm ripping you off, right? So it's not necessarily the price, and it's not necessarily, you never want to devalue the price. Oh, I can't charge the customer this because they can buy a new cable for this. No, the job is worth what the job is worth. The question is, what other options are there and how much do those cost, right? Because it's about value. What am I getting? What's the quality of repair versus the money I'm spending? And this is true with anything. So in this case, I'm giving a quality repair that's going to last the life of the vehicle or the life of the cable just as good as if I put a brand new cable on. I'm not afraid to charge for that. It takes special tools, special things, everything else to do it. I have no issue charging my time for doing that. But by the same, and the labor to do this is not much more than the labor to do this. The terminal's a little bit more, the heat shrink's a little bit more, but again, it's not exponentially higher. It's like $10 more to the customer. I mean, it's not like, OMG, we're gold plating the thing. But anytime we do a repair, we need to really look at options. And I do this with my customers. I'll price it out, new cables. I'll price it out, fixing the existing cables. I mean, what do you want, door number 1 or door number 2? I grew up watching game shows, right? Door number 1, door number 2. What do you want? You want the bass boat or the new kitchen? I mean, which door do you want? And I think that really, it does 2 things. First of all, it helps customers make the decision that they're comfortable with and is right for them. The other is the customer is going to feel good when they pick up the car and I charged them $60 for putting this on, because they know I saved them $140. If I just gave them the option of $60 to put a battery cable on, they're going to be calling around and finding someone who will put one of these on for a fraction of the price. We're not comparing apples to apples anymore. We're not, any of that stuff. So it's really important that, if you're doing repairs in a shop, you're doing repairs for other people understand the value of what they're buying. Because if people don't understand the value of what they're buying, they feel ripped off. And I that's true for me. That's true for anybody. And the other thing is people will spend a tremendous amount of money on something they want. We hate spending any money on things we need. No one here gets excited about paying for their cell phone bill. But yet we all want a cell phone. So we might have bought a better phone than we needed to just make phone calls because we wanted a cell phone, right? Or you wanted features on it. But you hate paying the bill every month because you have to pay the bill, but you wanted the phone. You wanted the phone you bought in many cases. So again, it's the want or need. People hate paying their mortgage, but they need to live in a house. But boy, they'll spend twice that much to go on vacation and feel awesome about it. And the vacation only lasts a week. You're living in your house all month, right? So we hate doing things that are a need. Just human nature is, it's drudgery. I'm just working for the things I need. We love doing the things we want. right? And that's why people have a different experience spending money on Coke than they do spending money on a staple that they need, or cleaning supplies or something like that for the house, right? Coke is, I want a Coke. Or if it's beer, I want a beer, as opposed to, I need more Pine Sol, I need more 409, I need laundry soap, I need, no one wants those things. We need those things, but yet we'll spend more money on things we want and feel great about it. So one of the things in automotive that we really dropped the ball on is we do not spend the time a lot of times educating the customer so that they're getting what they want, not just what they need. I've had customers that show up that spend $4,000, $4,500 on me putting a transmission in their car, and they're excited. They can't wait to get their car back. I mean, they are happy. I've also seen where people come in and spend $1,000, $2,000, $4,000 on a car. I made the wrong decision. I shouldn't have fixed it. I know it's not your fault, but I wish you had, I really had buyer's remorse, yada, yada, yada. Same money, same outcome. The difference in one customer's excited, the other customer's feeling like they were, drugged down this path and had no choice, and they're a victim, and it's horrible. Where do you think that changed? It changed by the person handling the sale, the person who was talking to the customer, really finding out what the customer needed from the vehicle instead of just selling the vehicle, the customer product. What's your goal for the car? How long do you want to keep the car? What condition's the car in? Well, I was planning on keeping it for another 3 years. Well, have you done work on the car? Oh yeah, I did. Rebuilt the suspension. I did brakes. I spent $2,000 on struts. I did all these other things. So it's in good shape then. Oh yeah, it's in good shape. This transmission, I don't know. Well, let's run the numbers. Here's how much it is. We looked over the car. You're right, it is in good shape. And I have customers, well, what other things can break on the car? I said, well, all kinds of things that can break, but you've already done this, this, and this. The engine appears to be in good shape. This is how much an engine is if it does go south. Here's how much new cars are. What do you want to do? And I've had customers go, you know what? $4,000, and I'm going to be able to drive the car for another couple of years, and I like the car, and I've already invested money in other things because I've maintained it. They're excited because I just saved them from spending 20 grand or 30 grand on a new car. Other customers, they haven't maintained it. I've actually told them, you know what? We can put a transmission in this. We can get this running again. Your brakes are gone. We know the suspension is horrible. You need tires. Really, this car needs about 7 grand worth of work to get it back to where it's reliable. And I would not want to put a transmission in it and then have you go out and not realize that. And I've had some customers go, thank you for being so honest. Let me pay you my diag time. And they show me their new car. I've had other customers that go, how much would it cost to do everything to get it in shape? And they end up spending 7 or 8 grand. And you know what? They're happy spending it because what? They decided to do it. It was their idea. So I've always been of the opinion, if you inform customers, you let them know the benefits and let them decide really what they want. And then you have happy customers when they're giving you money. I mean, what a great deal. And they're getting the car back. So it's a good thing, because there's 2 parts of this. One is did you fix the car? The other is the customer happy you fixed the car? And we used to always say in the shop, we're in the happy people business. Because if the customer's not happy, it doesn't matter how good you fix the car. They're still going to slam you on Yelp. They're still going to be mad at you. They're still going to, even if you fix the car perfectly, correct. If they're not happy, they're not going to be satisfied. And this is true with friends, neighbors, and family also, by the way. As we're coming into the holiday season where we might see those people who we worked on their cars. In order to replace the battery cable, and the cable must be sealed. Is that true or false?
True.
True, absolutely. So you heard me talk about I can be physically connected, but not electrically connected. Now we can see here, look at the amount of corrosion in this cable, but yet the connector looks pretty good. So this cable probably should have been replaced if it could have been cut back further. But in this case, this car came into a shop and customer put a new cable end on and the car still wasn't starting right. And what we do is we hooked a voltmeter up And we're dropping 1.15 volts through that connection when you try to start the car. Remember, I'm not going to be dropping voltage there unless I try to use current. That's a big connection. The only way I can really check the voltage drop there is to turn the starter. Well, now I combine the voltage drop here with the bad battery cable. Really? You're blaming the poor starter? Let's go down and check the starter and see how many volts it's actually getting. And when we did, we found the starter was getting like 8 volts. Poor starter. Well, you know what? Let's get some voltage to the starter and then see how the starter does. I've done this test on cars where I've actually seen 7-8 volt drop across that. And it's tight. So the whole visual of, hey, it looks tight. Hey, I wiggled it tight, so I know it's good. I don't know anything's good till I put a meter on it. And this is really just to drive home that point. This is a big connection. It's clamped together. And yet, if there's corrosion in there, I don't have a good electrical connection. If the tapers are not correct, I don't have a good electrical connection. So in a battery cable, posts are tapered. So they're wider at the bottom, narrower at the top. Battery cable ends are tapered. They're designed to seat in and have a good contact surface. If one of them has an angle like this, and the other has an angle like this, you don't have a large contact surface, you're going to have a voltage drop. So I've seen people improper clean battery cables, and now the posts are straight up and down. That's not going to work. I've seen people improperly clean battery cable ends. Again, the angle's wrong. It doesn't work. So I've had them where they go on, but they're not, the angles don't match. So I'm getting this, or I'm getting this. I'm only getting a small connection point. I'm not getting a solid connection between the two pieces. So they do make special battery tools. This is a couple of them. And I keep forgetting to put the other tool in here, the spreader. So they do have, because this is out of one of the books. So here, just using a regular wrench, they have battery pliers because sometimes these round out. Here's a special puller for removing a battery post. Once the battery post is removed, you see how far this nut backed off right here. We actually use a special spreader to spread the battery cable back out. And I'll go grab that spreader right now because I forgot to throw the picture in. And you folks that have been able to come down to campus with me know I love show and tell. So this last week, they got me to go over to the tool room and pull several things out and show them. So first thing I have up here, this is a battery cable spreader, cable on spreader. And see how it pivots. So you put it in and pivot. The part that opens up is where the bolt goes. So where that bolt is down right here. I'm going to put the open part where the bolt is, put it in, and then spread it. If you notice how this is actually tapered, see how it's not just straight up and down. There's a slight taper to it. So this goes in and then spreads it. If I put it in backwards and I put this in where the cable's coming in here and then spread it, I'll break the battery cable end. So this right here is how we spread them back out. So we use the puller to pull it. I use this to spread it. Why do I want to spread it? Because I want that battery cable to come completely down on the battery. So here is a battery cable cleaning tool. This is a wire one. We have some of these on campus. And if I pop off the other end of this, it has a brush that goes in and cleans the inside of the cable. So the brush type is the only kind I can use on the steel cable ends, like the Asian manufacturers use and stuff, and some of the domestics use where it's actually steel. I can only use the brush. For the lead ones, we normally use a tool like this. So this right here is tapered. This has little cutting teeth. So not only does it clean it up, but it actually resets the correct taper on the battery cable. So I put the battery cable on this and I turn it, and now it's not only cleaned up, but I've also got the right angle for it to go over the battery post. This also has two ends on it for cleaning. This right here is my negative, and there's my positive. You can see my positive is a little bit bigger, and they're done. So this actually goes on, and again, we'll cut the post a little bit. This is a scraper, so it's going to scrape it off, but it's also going to help reform the post. So remember, lead's very soft. So now I've reformed both the cable and the post, so I can get a really nice electrical connection on it. If I'm working on a side post battery, obviously I can't use this or the blue one in the picture. So this is what a cleaning tool looks like for a side post battery. So here, this has little barbs on it. This would go where the bolt goes in, and you just put it over and go back and forth, and it cleans up the lead for the side post battery. This side is a brush, and you put the battery cable here. The bolt goes down the center of it, and I can clean the cable. So this right here is used just for cleaning side post batteries. On side post batteries, one of the issues we have is being able to jumpstart the battery. Sometimes it's really hard to get into where those cables are. There's not a lot of space, and GM used these forever. So they actually make a tool. This is it right here. And it actually goes, it's spring loaded. It's just one piece of brass or bronze, probably bronze, goes over and it goes around the battery cable. Now I can put my jumper cables or my battery charger right on this. And it allows me to go down in very tight space and get a good connection on a side post battery for charging up a battery. So we're seeing the tools helpful.
Yes. Yes.
So I got lots of tools. And some of these, like, oh, shoot, this is probably 35, 37 years old. This has got to be equally as old because I bought the set at the same time. So I probably bought the set in like, I don't know, probably 84 is when I bought these. And that's in a shop they've held up that long. That's pretty amazing. So let's jump into high voltage batteries a little bit. So high voltage batteries also might be called a battery stack or battery bank. And what we find is high voltage batteries are actually made up of a lot of low voltage batteries, sometimes hundreds of them. Store chemical, electrical energy for starting the internal combustion engine. We use them for full electric propulsion. In some cases, provide 12 to 15 volt DC for electrical accessories and conventional electric circuits through a DC to DC converter. So what we're using is we're using a DC to DC converter to go from several hundred volts down to 12 to 14 volts to operate our lights, operate all that stuff. So all these systems have a DC to DC converter. That's also what charges our 12 volt battery, is that DC to DC converter. The only difference between a hybrid vehicle and an electric vehicle, and I mean, there are some other differences, but the main difference is a hybrid vehicle has the ability to recharge the batteries from an external source while you're going down the road. So whether that's a hydrogen fuel cell, whether that is a gasoline engine or a diesel engine, we have the ability to recharge those batteries going down the road using similar sort of fuel. An electric vehicle works exactly the same way, except for we can't charge the batteries. So there are different types of hybrids. There's parallel series hybrids. There's some other stuff that just assist. There's other ones that run completely off the electrical. But really, the systems themselves, the batteries, the motors, the inverters, the DC to DC converter, we have those same components, whether it is a fully electric vehicle or whether it is a hybrid vehicle. So really the main difference in the technology is the engine, is the gas diesel engine or a hydrogen fuel cell. When we look at the motors, when we look at the batteries, when we look at those things, that technology is very consistent. That's not to say each manufacturer doesn't do some things differently or has some different components or different motors or different voltages. Of course they do. But when we look at it from a technology standpoint, it's the same. So when I talk about batteries here and I talk about hybrid batteries, the rules are basically the same if I'm talking about, a Tesla, or I'm talking about a Jaguar E, which is fully electric, or a Range Rover E that's fully electric, or a Chevy Bolt. The Chevy Bolt and the Chevy Volt are very similar. The difference is one has a gas engine and one doesn't. Now, obviously, there's more differences than that because they're shaped differently and the parts are different. But if we're talking about the theory of operation and how these things work, not that much different, really about the same. And yeah, you had a question?
Yeah, what says on the bottom, a DC to DC converter?
Yeah, so what a DC to DC converter does is it's taking our high voltage and making it low voltage. So I'm taking 200, 300 volts, and I'm going to make it 14 volts.
Oh.
So very similar to what I would do like with a transformer for my train set, right? I'm going
it
from
lowers the
110
voltage,
volts,
is it?
and I'm going to go down to 13 volts.
Oh.
And then in case of my train set, it, you can do AC to AC or AC to DC or those kind of things. But we're using no different than probably what's plugged into a calculator or what charges your cell phone, right? We're converting that 110 volts AC to DC to 5 volts DC to charge your cell phone. We're doing a conversion. In this case, the conversion is from DC to DC, not AC to DC. We do convert AC to DC through what we call an inverter, because all of our motor generators on a hybrid vehicle are AC. Our batteries are DC. So I have to constantly convert DC to AC and AC to DC. And I'm doing that whether it's a hybrid or whether it's a full electric vehicle. Doesn't matter. Because the motors are AC, the batteries are DC. We have to constantly convert back and forth. So if I want to work on these vehicles and be safe, one of the things that manufacturers generally have us do is disconnect the high voltage battery. So here we can see there's a shipping service, unlock, and then a lock. For high voltage operation, here's no voltage. So we would turn this into different positions. This is a Toyota one that several manufacturers use. It pulls out when it's out. The battery no longer has any power. This is a BMW one here. This is GM, and this is Honda. Honda gives us just an on-off switch. But what's interesting is you cannot take this panel off unless you turn this off. So if you're doing testing, and I almost got myself in trouble with this once because I was doing some testing, I had to turn it back on with the panel off. I'm doing some testing, found out what's wrong, went to start taking it apart and remembered, oh yeah, shoot, it's still live. So even if you know it really well, mistakes can still happen. That's why we have safety precautions. We always want to verify a system is disabled. So if I'm going to verify it's disabled, I'm going to use a voltmeter with Cat 3 or 4 leads and verify there's no voltage present. Once I verify there's no voltage present, then I can take off the safety gloves. So the gloves you see right there, there's actually 3 parts to them. There is an internal cotton glove. There is a rubber, for lack of a better term, lineman's glove that goes over that. And those have to be tested every 6 months and certified. If you buy brand new ones, they're good for a year. And the cost of buying brand new ones is almost the cost of getting them certified. So most shops just buy new ones once a year and don't worry with the certification. And then the outer glove is a goat skin glove. Goat skin is used because we want to protect the rubber glove from any pinholes. But goat skin is much more flexible than traditional leather made from cowhide or heavy duty leather, which is made from elk hide. So what the gloves are made out of really determines how much flexibility you have in them, as well as how well they hold up. So deerskin gloves are also very flexible, but we use goat skin for this. So the type of material really makes a difference in how the glove can be used. And you can imagine it's kind of hard to grab a hold of a 10 millimeter nut with this and thread it onto a shaft. So it's really hard working with these gloves on. So we really want to use these gloves to verify the system is safe. Once there's no power there, then I can take the gloves off. Different manufacturers are going to recommend differently. I've seen some programs where they're having you do everything with the gloves on, which is just not practical. I'm a big believer. If I know there's no power there, why do I need to wear the gloves? If I work on my panel at the house and I kick the big breaker off and I take my meter and prove there's no voltage going through the breaker and there's no longer any power in my breaker box at the house, why do I need to wear gloves when I take breakers off or put wires on? There's no power there. I'm safe, right? Where it becomes dangerous is if someone else can turn on the power, or if I just flip the switch and didn't test to make sure the switch worked. And yeah, you got your hand up, June?
Yes, Mr. Brian, how long is typically the capacitors to go discharge and drain?
Normally about 5 to 10 minutes. It doesn't take that long on these. So if they're huge capacitors, they're 2,700 microfarads normally, and there's 3 of them. And they're pretty good size. I got I have some of them. You can see I have an inverter in the classroom and you can see the capacitors. They're pretty good size. But they do normally discharge in about 5 to 10 minutes. So they although they're big, they don't hold their charge very long. Good question.
Okay.
And that's another reason why we test. So I talk about voltage verification measurements, no PIDs. What I mean by that is don't rely on a scan tool to tell you something has 0 volts. Use your meter. Prove it has 0 volts. Now it's safe to work on. And I do this. I've worked on, I'm certified in hybrid. I've worked on a lot of hybrid, a lot of electric. I've done technical editing for books written on it and classes done on it. And I still get a meter out and make sure it's dead before I put my hands on it. That being said, go ahead.
Is there any certification, ASE certification for hybrid vehicles?
There is. It's ASE L3. And currently, I think there's somewhere around 1,700 technicians nationwide that have that certification. So about 1,700 technicians nationwide are certified. That's not
And
that
that's
many. is it?
nationwide?
Nationwide.
That's not very many, huh?
No, not when you figure we have I think the last number I saw was 1.2 or 1.3 million hybrid vehicles in California, and another 300,000 or 400,000 strictly electric vehicles in California as far as registered vehicles. So even if that was California, that'd be 1,700 technicians for 1.7 million vehicles. That's a lot of vehicles per technician if only certified people worked on them. But no, that's nationwide, 1,700. Now, of course, the dealers have their own certification programs outside of that. So the dealers, if you're going to the dealer, the only technicians working on those vehicles that have gone through the factory training for the hybrid system. But if we're looking aftermarket, and if we're looking at actual, ASE certification, there's only 1,700 people certified, approximately. That's pretty amazing to me. It also tells me in this day and age, if you got that certification along with some other certifications, you're probably pretty marketable going into a shop.
Yeah, I'm sure it does.
I'm old and don't work as fast or as hard as I used to, but I bet you I could get a job tomorrow. If I wanted to go back to the shop. And
Ron, you bring a good point. I don't want to go out the subject, but why do you think there isn't a lot of Texas? Is the understanding of electricity?
Part of it's the understanding of electricity. Part of it is the need, of doing it. I think a lot of it is that many people do not invest in themselves. So they get the certificates that maybe got them in the door, like a break or G1 or something. And then stop getting certificates because, oh, my boss doesn't care if I get them or not. Well, I'm probably not going to work for my boss forever. And I care if I get them. Okay. So the ASE certifications are something that I own. I mean, they're part of me. They're my certification. They're my resume, for lack of a better term. Why would I limit my resume to what my boss wants me to do when he's the one who doesn't want to give me a raise, right? Because the reason I'm going to leave is either I can't stand my boss anymore, or I'm not making enough money, right? I mean, those are two of the highest reasons that people leave jobs. So, and the reality is most people aren't going to get a job today and stay there for 30 or 40 years. So odds are you will be changing jobs at some time. And the old saying in the auto mechanics industry is that's why toolboxes have wheels, right? If I'm not happy here, I can back up my trailer. My toolboxes have wheels. I can be working somewhere else tomorrow. So it's a very different business than a lot of businesses are. And so I think a lot of people just don't invest in themselves. They don't take that pride. I think some people see it as, yeah, it's a job, but it's not necessarily a career. And I've always treated it as a career. I've always taken a lot of pride in my certifications, pride in my training. And that pride has had employers want to hire me and want to pay me. And it's also meant that I was better at doing my job. Every ASE test I've studied for, I've learned stuff. At this point, it's more a matter of just proving I know it. And I have to prove it every 5 years. So some people, and there's nothing wrong with this, some people have to go and they study for every ASE test they take. Last time I had to take 22 ASE tests. There's only one I studied for, and that was my natural gas test, because I knew there was some new, it used to be a lot of propane and stuff. And I knew that they'd done some changes to it. And sure enough, they'd moved it over natural gas and fuel injection. And there's a lot of regulation stuff they expect you to know. And I don't do it every day. So it's a matter of, what's the minimum distance a tank can be, maximum distance, the different types of tanks, how often does each tank have to be certified, all that stuff that if you do it every day, you remember. I don't. So I study for that just to get the regulation numbers, because you got to be if you're less than 8 inches away from a heat source, you have to have a heat shield. I mean, and they're going to test me on that 8 inches. I know it. So I go through and read the study guide for that, for the alternative fuels. That's the only one I studied for. Everything else, I just walked in, either I know it or I don't. Where there's other people that, they take 2 at a time because they need to study for every one. But hey, they passed the test. They got it doesn't matter whether I missed 0 questions or whether I missed the maximum number of questions, it's still the same ASE certificate. Right? So if I'm allowed to miss 11 and I missed 2 and someone else missed 11, I didn't study, but they did, it's still the same certification. Right? I mean, so it's about the certification. For me, I've just been doing it long enough that I'm just not investing the time studying on a lot of the stuff. I just know it. And I'm fortunate to be in that situation. But when I took my L3 exam, I did study for it for the first time I took it. I spent some time studying, because what's on it, I don't know. What's there? It's a lot of stuff. So I spent some time studying it. And I was real happy. It was a long test. It was probably the hardest test I've taken. I thought it was a really good test. And I ended up missing 2 questions. So I was pretty happy with that when that's a test that a lot of people that try to take it don't pass, that did study for it. So that tells me I understood it. It tells me, and it was actually a pretty fun test to do. I was glad I studied for it. I'll probably do a little bit of studying for it this time, just to kind of refresh a little bit. But on some of the stuff that I know they're going to be going, some of the terms, there's a lot of naming terms they use. And if you're not speaking that language all the time, you get rusty with it. So it's a constant evolution, a constant challenge. So I'll probably take some other ASEs. I took an ASE test on truck electrical accessories. I didn't study for it at all. I passed it, but there was a lot of questions on it I was not prepared for. So what it told me is this is something I need to go learn and understand better, because I wasn't clear when I took the test. And so some of the naming of switches, some of the function of switches, it's like, oh, I need to spend more time learning switches. I'm used to regular DC systems, not single pole, single throw, double pole, double throw, double throw, single pole. I mean, it's like, okay, this is a whole new language. I wasn't ready for that. I didn't expect there to be that many questions on it. And so I really had to kind of think about what I would use where and how it worked. But by doing that, it told me something I didn't know, So now so then I studied it, so I know it better. I'm going to study it more before I take the test again. Because it's something I learned that I don't know inside and out. And I think that by challenging ourselves, it makes us better. So I've taken a lot of ASE tests going, because I'm already paying the registration fee. I'm already there. Hey, there's this new test on light duty diesel when it first came out. Well, I know something about diesel. I'm going to sign up for that test. I'll spend the $30. Either I'm going to pass it or I'm not. But at least I'm going to find out what's on the test. And so I did a lot of them like that, where, you know what, if I fail, I find out what I don't know and I'll go study because I'm smart. I mean, you read a question, you know, when you don't have any clue what the answer is. And then if you passed it, it's, wow, I really did know that. So I've never thought of myself as really, I know it. I've always felt like I didn't know it. So I was always nervous when I took the test, but it was always interesting, even though I was nervous and really didn't feel confident, that I was competent and I was able to pass. So it's been a helpful experience. I didn't go get them all at once. I mean, I've built up ASEs over 35 years. And also currently I'm certified in 26 areas because that's just where I've ended up. And you had another question.
I was going to ask you the same thing where you just said there were diesel questions, a lot of diesel involved.
There are different diesel certifications. So for example, in the automotive series, there is the A9 light duty diesel, which deals predominantly with understanding common rail diesel and how common rail works. And it does have some injection pump question, but I think they're almost all gone now. So you need to know how computers work, how common rail works, that kind of stuff. So you need to know how the Ford system works, how which is not common rail. Not the new system is, but the old stuff is the HUCI, where they used oil to increase the pressure. So they had some stuff on the old Ford 6 liters and 7.3s in there. And then a lot of common rail questions. And then when I get to medium duty diesel, the book has a lot more questions on not just the fuel system and a mechanical injection as well as common rail. But you also see stuff on questions about sleeving cylinders or the different ways you rebuild a diesel in the truck compared to gas engines that you're pulling as more of a machine operation. So you get some, diesel diagnostic questions, you get some diesel, rebuild questions, things like that in there. And then there's engine performance. So there is, depending on what test you're taking, it may have no diesel in it because it's a gas test, or like air conditioning. We don't care what the engine is, right? It's an air conditioning question with the exception of hybrid because they work differently. But a lot of times they save some of those questions unless there's an overlap, like you need to know you use different oil in a hybrid system because of the electricity. So safety things, you'll see stuff going, but you're not going to go take like an A8 engine performance test. There's not going to be any diesel questions on it. It's going to be strictly gas. So they put all the diesel questions in that diesel certification. And actually you don't need the diesel certification for the light duty for cars to be master certified. The A9 is an optional. It's not part of the master. I took it because I expected the state of California to require it to smog diesels. And since I was there renewing, it's like, I'm going to get ahead of the curve. I think the state might require this. Same with my F1 for alternative fuels, because we smog those. I was expecting the state to require that either to repair them or to inspect them, and they haven't. So I was preemptive because I was already there. I'm already paying the $36 for the registration fee. At that point, it's just, one more test while I'm always there. I'll kick down the extra 30-something bucks to take the test, or $40, whatever it was. I'm already there. I'm already sitting. Let me try this other test. And that's why I got some of those. It's just the kind of trying to get ahead of the curve. Where do I think the state might go with requirements? And it turned out they didn't go there, but I still got the certificate. So my ASEs have always been about me. Have I had employers reimburse me for my ASEs? Yes, I have. Have I had a lot of employers that don't give me a dime for ASEs? Yes, absolutely. But I've always done them because that was something that I wanted. It was something that I felt, just like the tools in my toolbox, it shows off the tools between my ears. And I think that's important. Good shops, high-end shops will want ASEs. The shops that say, well, we want ASEs, but if you know what a wrench is, we'll train you. Those aren't real good shops. I mean, you can learn some stuff there. You can get a job there. They're a good stepping stone, but they're not going to be a high-end shop. Because high-end shops are requiring those things. They want you to know it before you get there, because they don't want you experimenting on their customers' cars. So, you know, a lot of times in the automotive career, you start at shops that are not going to be the ideal shop you want to end up at, because shops that are willing to train you really aren't looking to pay or have a highly qualified technician. They're looking forward to bring someone in that they can make money on. You're going to get some training. You're going to get a chance to buy tools, but it's not going to be your final stop. Well, how do I get to the next stop? Well, one way is tools, another way is certifications. Otherwise, you're stuck at that spot. And a lot of people get stuck at that spot. Oh, this place doesn't require me to do it. Yeah, but do you want to be here forever? So back to the capacitor conversation, capacitor draining, system potential is the same, just with an open, voltage verification measurements. 3 major stages of development in hybrid batteries. First generation hybrid electric vehicles, which used, many of them were 42 volt, 145 volts, fairly low voltage systems. True high voltage systems, these are generally considered to be over 200 volts. And now we see lithium ion batteries in mass production. The next step we're going to see, it looks like, is solid state batteries. So lithium ion is already from the drawing board engineering standpoint being phased out, just not in the production standpoint yet. Lithium is horrible for the environment, mining lithium. So that is, you know, so if you think you're being green, having a lithium ion battery, yeah, you're not burning fuel to get from A to B, but the environmental damage to build the battery is huge. So currently we have 2 ways of mining lithium. They're looking at doing a 3rd way using geothermal out in the Salton Sea, which is going to create tons of waste. But in Chile, they use open pit evaporation with water. So it takes 1,900 tons of water to produce 1 ton of lithium. And out of that 1,900 tons, most of it's lost to evaporation, but it still leaves 750 tons of brine waste for every 1 ton of lithium produced. If you're mining lithium like they do in China, it's pit mining, you create 250 tons of ore waste for every 1 ton of lithium. So when you hear about, oh, the batteries are so environmentally friendly, they're so this, a lot of times we're looking at things in a very narrow field of vision. Not to mention how much carbon was produced to mine 260 tons, sort through the 260 tons to get the 1 ton lithium. And then what are you doing with the other 250 tons, right? So there's obviously some carbon used there. Same thing if we're in Chile. As a matter of fact, Chile is so severe, they're using so much water for lithium mining, they're having food shortages because they're using the water that they would use for crops for mining lithium because it's an export product and profitable. And so they are actually not able to irrigate the field, so it's starting to cause some food issues. So nothing happens in a vacuum. We learned that with Ohm's law. If I change the resistance, current or voltage has to change. I think that's true with everything. If we change one thing, something else will be affected. We just don't always know what that is right away. But really interesting, Nature did an article on lithium mining. Also, lithium currently is not recycled. So all this thing about, oh, you can recycle batteries, you can recycle batteries. We currently do not recycle lithium. We do recycle nickel metal hydride. When we are able to recycle lithium, it's like either 26 or 28 tons of recycled lithium to get 1 ton of usable lithium. What's the rest of the stuff? Waste, right? I mean, so it's, you know, it's a little more complicated. So dual voltage systems, 12 volts for conventional electronic circuits, and then high voltage for the AC compressor, motor, generator, inverter, and the battery. So we have a low voltage system that works like every other car out there, and then a high voltage system. Our high voltage system and our low voltage system are completely isolated from each other. They don't share any of the components. So my high voltage battery is not grounded to the chassis. My whole high voltage battery is completely isolated from the chassis. So, and it's completely isolated from my low voltage system, except for when we turn on the DC to DC converter. And even then it's still isolated. We're just allowing current to flow.
I have a question.
Yeah.
'Cause I'm just listening to you right now. I have you in my pocket, but you're talking about are you talking about the electric vehicles only right now, or batteries just all together, just
All better. So I'm talking about either hybrids or full electric vehicles. Both.
okay,
The high voltage system is completely isolated.
right. Alrighty, thank you.
You bet. Yeah. So battery positive and battery negative on our high voltage system never touch the chassis of the vehicle. So the high voltage battery is normally mounted in the chassis rear, often behind or under the rear seat or in the trunk area. They tend to mount them no further back than between the rear strut towers or the rear suspension or that D pillar. Because in the case of an accident, we don't want to be crushing that battery. So we want to have it in other ways. It's not going all the way back in the trunk. So they may call it the trunk area, but really it's not going back past where that rear suspension is. Economy vehicles may have one large high voltage battery. Larger full-size vehicles and full electric drive vehicles can be equipped with 2 or 3 high voltage batteries. And then we can take those high voltage batteries and either wire them in series or parallel. What are we trying to do? So you'll see we wire these several different ways. So here is a Toyota battery. And this is made up of many small cells, called battery packs, wired in series to produce high voltage current. So a Gen 2 Toyota uses 28 of these. And each of these little battery packs has 6 cells in it. 2 battery packs make up a battery block. There's 14 battery blocks. So you don't need to know this. I'm not going to test you so much on this as that you need to understand the construction, how we're putting this together. So we're making this of many small individual batteries. Each cell is its own battery. Nominal voltage on these is 1.2 volts. So the 2 different styles that we have of nickel metal hydride batteries are the Honda style, looks like a bunch of D cells put together. So Ford, Escape use these, Honda use these, a couple of manufacturers use this style. This is the flat style used by Toyota and others. And you can see here, we're hooking it in series. If you notice, there's a jumper wire here where the other jumper is at the back side. So again, we're going positive, negative, positive, negative, positive, negative, positive, negative, just like I did with my little batteries, except for here I have 6 batteries already taped together in series, and we're just jumpering the ends, positive, negative to build our voltage. On this system, we're doing the same thing. So this is going to be the positive of one battery, negative of the next, positive, negative, positive, negative. And we have little straps to connect the positive to the negative here, and then the positive and the negative back here. And we just keep strapping back and forth to put the batteries together. And here we can see where it's installed into a vehicle. So if I look at a wiring schematic for this, I can see right here, it shows the service plug. That's that orange piece I showed you we pulled out earlier. The service plug mounts between 2 of the battery units here. When we open this up, we no longer have a battery that's in series. I have 2 small batteries. I have one here and I have one here that would have potential between here and between here and here. But I do not have one big battery anymore. And I have no current flow that can come out here to the vehicle because it's an open circuit. We know we have no flow in an open circuit. Where the battery disconnect is in the middle of the battery right here. Any idea how much voltage is there? I'll give you a clue. I gave you the answer yesterday.
46.
No. What's the difference in potential between the positive here and the negative here when I put them together? If there was a difference, wouldn't I get a spark? Wouldn't there be, wouldn't I have smoke if there's no load between them? They're electrically the same. This is a several hundred volt battery, but right here, between here and here, there's 0 volts. That's why the disconnect's in the middle and not at the end where we would have several hundred volts. That's why Toyota does that. So some manufacturers do put it at the end. There's several hundred volts at this disconnect. That's why they're telling you to put on all the gloves before you take the disconnect off, because that switch is at several hundred volts. Toyota tells you to put the gloves on to take their switch out also, because they're emphasizing safety and not understanding. I know there's 0 volts there. So since there's 0 volts there, why would I put gloves on? Because I have understanding. So back, just like we talked about our first week of class, safety is important, but a lot of times they use a blank safety statement because it's easier to teach you how to be safe always than teach you how something works. Once you learn how things work, then you can figure out, do I need to do this step or not do this step? If you don't know, you should always do all the steps. You should always be as safe as possible. But I understand how electricity works. I know how a series circuit works, and I know there's 0 volts here. So if there's 0 volts here, why do I need gloves? On the other hand, if I'm working on another manufacturer that puts it at the end where it's coming out to the rest of the system, whoa, that's 300 volts there. I probably want gloves. So you see where Toyota has you wear the gloves because they don't want to explain how their system works. It's just easier to tell you, to train you to put gloves on. So again, manufacturers put rules in to be safe. They don't want to get sued. You should always follow those rules until you have enough knowledge to realize when they don't apply. So here's a little battery pack. So here we have 6 cells. This is from Toyota. 1, 2, 3, 4, 5, 6. Each cell is 1.2 volts for a total of 7.2 volts in each battery. Each block 14.4 volts because it's 2 of these packs to a block. And it's kind of hard to see, but one of these sides will say positive, the other side will say negative. This right here is the vents, because even though these have basically gel or paste in them, if I turn them upside down, they don't leak. If they get too hot, they can gas. And so I want that gas to be captured and removed from the vehicle. So consequently, we use sensors in here to measure temperature. So we do not overheat the battery while charging. So we're going to limit the battery's capacity both in driving and charging based on temperature in the battery. Here is a Honda battery, and you can see here where we have all the different groups, and these are jumpered, positive, negative, to come up with our whole battery. So you can see a hybrid battery is actually a bunch of small batteries, because we can only get so much voltage out of the specific chemical reaction. So in our lead acid battery, we got 2.1 volts. In this battery here, we get 1.2 volts for nickel metal hydride. So individually sealed, hold semi-solid electrolyte, acid, paste, or gel around the positive and negative plates, soldered or mechanically fastened to adjacent cells. So a hybrid battery with nickel metal hydride normally consists of how many cells in a little battery block? Right, what did I just show you?
I know the answer.
What is it?
Hold on, I'm thinking. The answer is how many? Okay, the battery. Read it to me again.
12.
Consists of
6.
how many?
6, right? So each battery is, we buy the little battery unit. See, I got 6 here. 1, 2, 3, 4, 5, 6. If I'm working on this one, 1, 2, 3, 4, 5, 6. So each of these individual pieces has 6 cells in it. And it's not the best written question, but I want you to know it because you're going to see it. Because when you do the PowerPoint review quiz, I'll make sure you got it. So nickel metal hydride battery pack, set of low voltage battery cells wired in series, has approximately 30 to 40 individual battery packs. I mentioned Prius is 28, even more for all electric vehicles. Now, one of the disadvantages of nickel metal hydride is I cannot fully, remember we talked about cycling rates, right? For 12 volt batteries, how deep we cycle them, where their range is. So nickel metal hydride, I can't charge to 100%. They don't like it. I can't go below 40%. They don't like it. So these batteries normally work in the 40 to 60% range. So one of the issues we have with nickel metal hydride is I can't charge it fully and then discharge it. So I'm carrying all this weight, but I can only use this little bit in the middle between a 60% charge and a 40% charge. I'm not using the whole battery. I'm only using that middle 20% of the battery. So that's why we don't see nickel metal hydride batteries normally used in plug-in applications. Plug-in applications are going to use lithium ion because lithium ion is able to charge up to about 99% and go all the way down to 20. So it has a much deeper cycle rate. I have 80% of the battery I can use. That's one reason why lithium ion was such an advancement. So even your display on the dash or your charger may say 100%, that's really only 60%. When it says 0%, you're really only 40%, right? You're only using that usable 20% in the middle, which works great when I have an ICE engine that's able to start and charge, let it use it, charge it, let it use it, charge it, let it use it. Very, very efficient for that. But if I want to plug in and go somewhere, that's a lot of weight to carry for only using 20% of the battery. So that's why lithium ion was such a huge advancement for plug-in applications. So that's what really opened it up for full electric vehicles and plug-in hybrids. Is now I have this battery that lets me go up to 99%. And sometimes we may only charge to 95. And you're thinking, why do we only charge to 95? Well, the battery can go to 100. But because the car is going to charge the batteries when I hit the brakes, I need to have some place to put that brake energy. So I don't want to charge it to 100 when I get here, because odds are as soon as I pull out of my parking spot, I'm going to be hitting the brakes pretty quickly. So I need to have some place to put that energy. So that's why they don't charge all the way to 100. So it's not like 95, 98, 99%. And then at 20%, we're done. So your 0 to 100% charge is actually 80 to 95 or 80 to 98% charge, right? So when we talk about batteries, 100% is not 100%. 0 is not 0. It's whatever that battery technology affords. So these have larger capacity. And I explained the difference in capacity. We're using 80% of the battery instead of 20% of the battery, different capacity. We're not using these systems at higher voltage. We're still using that 200-300 volt range, although there are some new systems out going up to 800 volts. So that's going to be interesting. The batteries themselves, the cells themselves make a higher voltage, which I'll get to in a minute, but the battery overall has the same voltage as what we're used to. So here is a Chevy Volt, and here is its battery assembly. It has over 100, I think it has about 100 battery packs, as I recall, in this 96 battery packs or 98 battery packs that are measured on the Volt. So a lot of these, and this is down the center console, and it is across the back. And we have a few electrical connections. You can see some electrical connections here, liquid cooling fittings, the other electrical connections. And then you see these holes right here. These holes are on the bottom of the vehicle. So to replace this battery, you put the vehicle, you disconnect these things. You put the vehicle up in the air, you undo all these bolts around the outside, and the whole thing drops out the bottom of the vehicle. And this is pretty consistent, whether it's a Nissan Leaf, a Jaguar, a Land Rover, a Tesla. They're all doing it the same way. They're dropping that. You have electrical connections and coolant connections inside the vehicle or underneath the hood or whatever you're going to disconnect. And then you're going to drop that whole assembly out the bottom. So you can see where this is quickly, unlike a Prius, Gen 2 Prius, where I can take the interior part, reach into where the trunk area is and pull the battery out. Pretty easy to get to in service. This is what? Much bigger, much heavier, requires some special tooling, a special lift for taking it in and out. So you see where that powertrain lift really comes in, Ricardo? So even though, yes, it's a powertrain lift, I can adapt it to do this because it has the capacity.
That's what I was thinking. That would be perfect for that.
So kind of forward thinking of me, huh?
Yeah, I was going to ask you about that. Like, you know how the Tesla's legislation and all this good stuff and not too many techs. I mean, we talked about this before, but I just want the students to understand the importance of electricity. You know what I mean? Like,
Right.
Not enough techs.
Not enough techs, and there's also a thing called R2R, or Right to Repair. Massachusetts is actually the state that seems to be the forefront of that. And that is suing manufacturers, saying that they cannot monopolize the repair information and we have the right to repair our own vehicles. So it's not just a shop thing saying shops have the right to have access to it, is that the consumer has the right to access the information on their vehicle. Now, that doesn't mean that information is free, but it does mean that they have the right to the factory scan tool to work on it. They have the right to the information to work on it. And so this has happened over the last 20 years several times. Manufacturers lose, they kind of do that, then they kind of make new rules and they get sued again. So there's just another round of lawsuits on that. Now, Tesla's the forefront of those lawsuits because they're really going after Tesla right now under right to repair. So this is, this is something that is, constantly in flux, but the argument is that people should have the right to be able to repair their own vehicle. Okay, they should have the right to buy the tools to do it. They should have the right to the information of how it works. And of course, the manufacturers are always arguing, oh, trade standards. If I tell them that, then anyone can steal our stuff, right? So you have the, trade standards, trade secrets, I can't share, versus no, we want to know how you did this. So you have this constant battle, and that battle has been going on for decades. So as we have manufacturers now that aren't sharing, they're actually rewriting the OBD2 regulations to include electric vehicles, which currently they don't, because they're seen as zero emissions. They're exempt from OBD2, so they don't have to have a DLC, 16-pin DLC. They don't have to talk to an OBD2 scan tool. They don't have to do any of that stuff. Well, guess what? The government said, well, that's a neat loophole there, but you've taken advantage of it, so we're going to close that loophole. So that's currently where they're moving, is making regulations for full electric vehicles for OBD2, which currently doesn't apply. So you can see, so it's always a cat and mouse game between the legislation, between the aftermarket and people wanting information and the manufacturers not wanting to share it. So here is a scan tool capture off of a Volt. So 288 batteries. If I had 1.23 volts per battery, 345 volts total. I don't have that. I have 96 batteries at 3.86 volts per battery. There's my 370 volts. Each one has a block of 3 cells. So I actually have 288 battery cells on this. But instead of wiring everything in series, what we're doing is we're taking 3 cells and wiring them in parallel. So I'm taking 3.6 volt cells, wiring them in parallel, and then I'm taking that 3.6 and wiring it in series to the 3 cells next to it, to the 3 cells next to it, to the 3 cells next to it. So this is a different chain structure. We have 3 cells, all the same voltage wired in parallel. Then these 3 cells are going to be wired in series to the next 3 cells and to the next 3 cells. That's where they're getting the capacity out of this. So this is what Volt does, and from what I'm saying, is not common for lithium ion on plug-in applications or full electric applications, because now we're getting what? More depth. So instead of having a lot of small batteries in series, where yeah, I built the voltage up, but I still have a small amount of amperage. It's like taking a whole bunch of 9 volts and hooking them in series. Yeah, I've got 200 volts, but how much work can I do with this before these batteries are bad? But how about if I take those 9 volt batteries and wire them in parallel first, 3 of them in parallel, and then hook them in series and come up with the same voltage? Now I have a lot more amperage capacity. So this design allows for a lot more amperage, which is why we see this with lithium ion on plugins. And this is why Chevy did this. So if I'm looking for a problem, I would want to be looking to see who is not the same. So if I look at all these battery cells, we can see they all have the same voltage. If a battery cell doesn't have the same voltage, that's a problem. So odds are they're not going to have exactly the same voltage as I accelerate, as I decelerate. So there's a range on different conditions. So as a rule, we say normally plus or minus 10%. Some manufacturers are stricter than that. Some are looser than that, but it's a good rule of thumb. So 10% of 3.86 would be 386 millivolt difference. If I have a battery system that works on 14.4 volts, 10% is 1.4 volts. So you can see that 10% is kind of a good rule of thumb. We shouldn't get concentrated on gee, is 400 millivolts okay or 300 millivolts okay? A, we're looking for what's not the same, and the higher voltage that the system uses, the more, the bigger the spread in total numbers is going to be acceptable because it's all about percentage. So in this case, the battery pack for nickel metal hydride is 7.2 to 8.2 volts, depending on state of charge. For lithium ion, it's 3.4 to 3.9 volts. The static voltage of a lithium ion battery is 3.6. Different chemistry, different voltage, right? So the chemistry defines the voltage. So we saw a lead acid battery, 2.1 volts, nickel metal hydride, 1.2, lithium ion, 3.6. So you kind of wonder sometimes why these tools you buy, why is this a 9.6 volt tool? Why is this 20 volts, or why is this 18 point something, so, or 14.4, right? Why did we have these odd numbers? Well, it comes down to battery construction. Right? So 3.6 volts, how many times can I multiply that out? So we have these numbers. So what we've seen now is we're getting sloppy and we're rounding and calling it 20 volts, or we're calling it 18 volts. But in the early days, we had systems that, why do we have this decimal? Why is this a 9.6 volt system? Why is this a 7.2 volt system? Has to do with battery technology and the batteries being used. Banks of batteries wired in series produce anywhere from 1 to 300 volts DC. Battery packs also have fuses in them. So we have high voltage fuses, protect against shorts, excessive current draw from each group of cells. So we do have high voltage fuses, just like we have low voltage fuses. The high voltage battery has its own computer. That computer is in charge of maintaining battery temperature, as well as charging, setting faults, looking for bad cells, those kinds of things. Can activate air, water, refrigerant cooling systems. Look at the temperature sensor. So we have anywhere from 1 to several temperature sensors, depending on the battery. So old Honda batteries, early 2000s, had 1 temperature sensor. Gen 2 Prius from 2004 to 2009 had 3 temperature sensors. Toyota's kind of stuck with that. We see other systems that have 5, 10 temperature sensors. Right? How many different places in this battery? We know that the center of the battery always gets hotter than the edges of the battery. So the cells tend to fail in the center first due to heat. The power cables are large conductors coated in bright orange. High voltage AC cables convert the inverter to the AC compressor. High voltage battery cables connect the DC to the high voltage control module and the high voltage motor generator. We have 3-phase AC from the power control module to the motor generator. So as I'm looking at these cables, I got 2 really big cables up here. Those are going to my battery. I have 3 smaller cables down here. And these 3 smaller cables are going to a motor. In this case, they're going to an AC compressor. This is still the same voltage. These smaller wires can kill me just as much as the big wires. And if I back up, not that this picture doesn't show it. I have another picture with a small wire in it. So it can be the smallest wire. Like when we were testing the DVOM, we were looking at those real small wires with orange. Those real small wires can still kill you. They have the same voltage. At this voltage, 5 milliamps, 10 milliamps is enough to kill you. And those of you that have been doing the in-person labs know 5 milliamps is not very much. So I'm going to finish up as promised with a vehicle that came into the shop with a code. And this one had a code for a battery. And I don't trust codes. Codes are a symptom, not a reason to replace a part. So I want to prove the battery's bad and give a good recommendation to my customer. So what I'm looking at here is I'm looking at all of my battery blocks. There's 14 battery blocks. And I'm also looking at my engine RPM. So right here is my engine RPM. It's going to look different than the others because I'm measuring something different. I'm not measuring a battery. I'm measuring the speed of the engine. And on each of these blocks, it has time, just like a lab scope, except for here I'm graphing from a scanner. I have my time, and then I have my amplitude. In this case, my amplitude is my voltage. And on the scan tool, the voltage does what we call auto ranging. In other words, it's only going to show the lowest number and highest number. It's not going to go from 0 to 20 like our lab scope does, or 0 to 50. It's just going to show the numbers that it's recorded during this movie. And what I want to look at is I'm looking at, is one of these cells bad? Or one of these blocks of cells. There's actually a block of 12 cells. And characteristics of a bad battery that I know from 12-volt batteries is 12-volt batteries lose their charge faster and charge up faster than a good battery because it has less capacity. So it's going to, the voltage will go low much faster and go high much faster. So I can look at the numbers and try to find the problem. I can also look at the pictures. And if I just look at the picture here, and if I look at all these pictures and don't pay attention to this one, because we know this one's different, very quickly, you see one picture doesn't look like the others. Everyone see that? So right here, battery block 7 does not look like the others. These all went up, and then I got a sharp drop. And see, I went up, sharp drop, sharp drop. What do I have here? I got this kind of, that's not a sharp drop. So that's one of the advantages of graphing, is that instantly your eye is drawn to what doesn't look the same. When I look at the numbers, I see the maximum voltage is 18 volts. Did anyone else go over 18 volts? Nope, no one else went over 18 volts. I went down to 15.61 volts. Did anyone else go under 16 volts?
What tool are you using?
This is a Snap-on Veris. So the Veris allows me to graph up to 16 things at a time on the screen, which is why I like it.
Is that a scan tool and a what is it called? A stethoscope and a meter?
Yep,
So-
yeah, so it has a 4-channel
everything on that.
scope in it, has the scan tool in it, has all the bells and whistles. This is their top line tool.
That's what I want.
And it manipulates data. It does a lot of things I really, really like. And that's why I have it. Matter of fact, the one I used in the shop, this one, I wore it out. The battery went bad and the hard drive went bad. I finally wore the thing out. It was, the tool was sunsetting. They were going to update it anymore. So I traded it in and got a new one for only $2,200 more than to fix the old one, which I thought was a great deal, even though I'm not working in a shop every day still. And I use it. I'll bring it down to the lab because it has 4 channels. So I'll bring it down so we can look at all 4 parts of a relay and some of that stuff in the lab where we can see it all on one screen. So I'll probably bring it to the lab next week. I'm on my list this year to buy one for the school. Currently, the school doesn't have one, so I use mine for my class because it does some things really slick. But if I'm looking here, no one else went to 15 volts. I only got 2 that went below 17 right here, 16.99, 16.98. This battery block is totally bad. So now it's, how do I fix it? In a shop, I'm going to recommend we put a whole new battery in it, just like we had our conversation with coils, right? When one goes bad, you replace them all. The reality is, can I go in and replace just this battery block? Yes, I can. I can physically do that. And I can tell you a lot of the taxi drivers, a lot of the Uber drivers, that's exactly what they're doing. Because they're taking their car apart once a month and replacing the next one that goes bad. And they're looking at what? It's a couple hours of my time, and it's $30 from the junkyard for some new cells, compared to a couple thousand to $1,000 or $1,500 for a whole, or $2,000 for a whole new battery. Totally, they get it because they're trading their time for money, right? My customer doesn't want to trade their time for money. My customer wants their car fixed. So in the shop, I only put in the whole thing, even though I know how to rebuild them, I know how to sync them. The other thing is, all these other cells are pretty well matched. What makes you think the used ones you get, because you can't buy new ones, are going to be matched to these other ones? So you may still have a code when you're done. The one advantage of graphing this also is I've done this for students, because I've had students that drive Uber or do these other things. And I pull this up. They got 3 blocks that are bad. Here's the one that set the code. Here's the other 2 blocks that are going to be bad in the next week or 2. So if you're going to do it, go do all 3 blocks right now. Go, so that we're only taking it apart now, and you're going to get, so, knowledge is always power. I like to do this because this way I can let my customer know, here's what we found. We confirmed the battery's bad. Here's where the battery's bad. The other thing this does is I can put a battery in And 3 months from now, this same block, number 7, might be bad. What are the odds the new battery I put in had the exact same block bad as the one I just took out? Slim to none, which means something else had to be causing the problem. And what they do on Toyota, I don't think I have it on this picture. Let me see, does it show it? Yeah, so what we're seeing here, all of these pins right here are sense wires going back to the computer, where it's monitoring the voltage on each of these. That's where my PID comes from. If there is resistance in there, is it going to under measure the voltage and therefore overcharge the battery? Absolutely. So if I have a corrosion or a wiring or connection issue on one of these, it'll cause the new battery to go bad on the same cell. It's rare that that happens. We don't test for it every time, but and I know my battery's under warranty, but by the same token, if I have the information when I do the original repair and 6 months later, that same cell goes bad, do I need to start thinking about what else could cause that cell to go bad? Absolutely. And so, you know, again, every time I do a diagnostic like this, I save the screen. I can show it to my boss. I can show it to the customer. I can use it months later or a year later or 2 years later when that car comes back. Did I miss something? Is it something completely different? So now I have a lot of confidence. You know, hey, you know, we think you misdiagnosed it. No, last time it was cell number 7. This time that battery that you made me put in 3 months ago, it's cell number 13. It's block 13 is bad. It's not even the same block. You just got me a bad part, right? But if I didn't have this information, how could I be sure of that? So we didn't get into starting and charging today, which is fine. I'm glad we were able to spend the time on batteries. We covered a lot of great stuff. And I normally allow 2 days for each anyway, so it's not a problem. But hopefully you guys got some good information on batteries today, good information on battery testing, and learned a little bit about high voltage batteries where they're not so scary once we break down and see what they're made of.